Okay, good morning once again, class. Today we're going to continue our discussion on multiple linear regression. And we said that this model is one of the most, I'd say, common or popular models in statistics or econometrics because in this model, in this statistical tool, we want to establish if there's any relationship between a particular variable of interest called your response variable or explanatory variable or dependent variable as and its relation with other uh, covariates, other independent variables or explanatory variables. Okay, did I mention a while ago explanatory or dependent? It should have been explained variable or response variable. Okay, so the equation is like as we mentioned last time. So the equation is y sub I, which is the your dependent variable, is a function of several explanatory variables, x sub 1 up to x sub n, depending on the number of explanatory variables that you have. Okay, and beta null is your intercept. This is the value of your average value of your dependent variable, of your response variable, if all the predictors are all equal to 0. Which means that this is just the average. This is the average level of your response variable if there were no predictors to be used. So when we look at beta null, uh, this is the value when your x1, x2, x3 are all zeros. Okay, so if we substitute zeros for all x1, xi's up to xn, then this will be reduced to 0, and then your y sub I will be beta null. Then this is just the average value if there are no predictors that's used for your model. Okay, and each one of these, beta 1, beta 2, up to beta sub n, are all your slopes. They are the marginal impact, marginal effect of your independent variable on your dependent variable, assuming that all all others all others remain the same. Okay, so we'll look at that in greater detail when we have examples of this model. And the epsilon sub I, this should actually be epsilon sub I. Let me uh, let me see. Where's my epsilon? Here, epsilon, and then I will put an underscore here, underscore, and then I. So that will give us the okay here. You notice that there is now this subscript when I place here underscore I. Okay. All right. So, and if you take a look at this class, so this was our equation. And then here, notice I placed here where this one. So this is a text. Okay. But we will not really go into that, but it pays to, because in your, for example, in your outputs, you will be required to, of course, explain your variables, and this will help a lot. This will help a lot. And as I mentioned before, this is called LaTeX, L-A-T-E, okay, L-A, let me write that here, LaTeX, LaTeX. Okay, it's pronounced as LaTeX because the X here is not actually, it's not actually English X. It's the Greek letter chi, C-H, C-H-I. So that's why, just like tech, technology. So you pronounce it as LaTeX and not latex. Okay. All right. Then last time we discussed that there are certain assumptions that we need that are that are that we have as far as regression is concerned. These assumptions are very important because violations of these assumptions might indicate that that the choice of a multiple linear regression model is not the proper model to use. Okay, so let's quickly review them. Linearity of the data, which means that when you look at the relationship between your y, your dependent variable, and each of the independent variables, they should be linearly related. It doesn't make sense to, let me just annotate that. It doesn't make sense, for example, if you plot your y here and your x, and then if you take a look at the relationship between them, and it's more, say, quadratic or a curvilinear relationship like this. And if you're going to use a model that's linear, okay, you can see that this is linear and this is more quadratic in relationship, then this linear model might not be the best model to describe y in relation to x. Okay, so this is very important, linearity of the data. Also, we have linearity of the parameters. And we discussed this last time. When we say linearity of parameters, we mean that the parameters beta, beta null, beta 1, beta 2, etc., they should be linear. Okay? They should not be expressed in, let's say, like functions like square root or e to the beta 1. Okay? Let me annotate that again. So square root of beta 1, okay, beta sub I, for example, or e to the beta 1. Okay, these are not linear in terms of the parameters or log of beta 1. Okay, so the parameters should be linear, which means that there should not be a square root here or a log here or an exponential here. Okay, so that's what we mean by linearity as far as parameters is concerned. And then we also have homogeneity of residual variance. The next assumptions look at the model itself and the characteristic or attributes of the residuals. we discussed last time that the residuals, which is epsilon sub I, is equal to the actual value of your y. Okay, we know we have the data gives us the exact value of y, and then we subtract the y hat, which is the model value or the predicted value. Okay, where are we going to get this? Isn't it that when we create a model, we will now have values of beta null, beta 1, beta 2, etc., the parameters. So when we have these values, when we have determined these values, we can now compute for your, when we substitute, okay, for example, for a specific observation, we have the corresponding x1, x2, x3, x4, okay? And when we substitute the betas there, and when we compute for the value of y, we have what we call the predicted value. So when we compare the predicted value, this one, and the actual value of y, then we have this residual. And then when we collect all the residuals and then plot them, they should exhibit constant variance. Okay, what do we mean by constant variance? If we plot the residuals, okay, let me say I'm plotting it, the residuals there. Okay, this is what we mean by constant variance, which we showed before. No? Unlike a variance that behaves this way, the variance is increasing over the values of x. Okay, this is a variance that is not constant. So we don't want this model because this residual plot tells us that our model was not able to capture the behavior of our data since you have a non-constant variance. Okay, so that's an important assumption of of a multiple linear regression. The variance should be constant. Okay, also another assumption for the variance, for the errors, is that they should be independent for this one. The residuals should be independent, and also the residuals should be normally distributed. So three things about residuals. They should exhibit constant mean and constant variance. And also, by the way, related to that is that the average variance should, the average or the mean of the variance should be equal to 0. Okay, so the expected value, so how is that written? So we write it this way: the expected value, okay, of your residuals given your x values, okay, these are your predictors, should be equal to 0. What does this mean? The expected value is simply your average. So when we get the average of all your residuals, it should turn out to be 0. Okay? And then also the expected value of the variance should be constant, so constant variance. And as I showed a while ago, the residuals should behave in such a way that they do not have a trend. They're not increasing over time, they're not decreasing over time, but they should behave in such a way that across several values of x, they should be constant. Okay, hindi sila nag-i-increase, hindi sila nag-decrease. Otherwise, we said that if their behavior is such, then we have what we call heteroskedasticity, hindi homoskedasticity. And we don't like a model where the variances are heteroskedastic, okay, because that violates our assumption of our model for multiple linear regression. Because if the residuals do not behave in such a way, then our model will cease to be what we call, do you recall the acronym for that class? I'm not so sure if I mentioned it in this class. Did I mention the blue model class? Kindly chat, please. Could, if I mentioned this, did I, class? Okay, yes, good. So we said that if the assumptions are met, then our model can be considered as a blue model, the best linear unbiased estimators. The betas are your best linear unbiased estimators. Otherwise, if some of the assumptions are violated, then we will have to check if the model is still blue, best linear unbiased estimator. For example, they might not be the best anymore, or they might not be unbiased. They may be biased. So we'll take a look at those conditions as we move on. All right, the packages that we'll be using is the Psych, PaceText, OLSRR, and the Stargazer. So this is just a quick review class. In order to install this, in case you haven't installed it, we make use of the Pacman package shortcut. Okay, so I load Pacman, and then from the Pacman package, okay, I use the pload. Of course, I don't need to write this Pacman. I can just use this functionality pload. Okay, and then let me just copy this. Control C, Control V. All right, and then I run this. And once I run this pload, it will now be automatically installed if I haven't installed it, and also loaded. So if I check here under packages, and let me see, let me check OLSRR. Okay, here OLSRR, you'll notice that it's already checked, which means this is already loaded. So OLSRR is a very powerful package for building OLS regression models. By the way, OLS stands for, what does OLS stand for, class? What does OLS stand for? Anyone? Okay, thank you, Ivan. Ordinary least squares. Okay, what does that mean? Ordinary least squares, ordinary least squares. Okay, I'll show them later as we continue with our model. But what's important here is this least, L-E-A-S-T. So that's the lowest. The squares refer to the residuals. So we compute for the residuals by comparing the actual value, okay, and the hat predicted value. Okay, so we get the residuals and then we square that. So that's epsilon squared. Okay, and then the line of best fit or the OLS model is the line which will produce the minimal, most the lowest squared of the residuals. Okay, so this one is just a computation of the sum. So we're just summing up your residuals squared. Okay. As I mentioned a while ago, we're able to compute for the residuals. When we have the model, we know the beta values, we know the parameter values. Then we substitute these values to get the predicted value. And then we compare the predicted value with the model value to get the residuals. Now, we don't base it on the sum of your residuals. Why, class? May I know? Anyone? Why are we not basing it on this summation of your epsilon of your residuals? Why base it on the epsilon squared? Why base it on the squares? Why not just get the minimum, the model that gives us the minimum sum of the residuals? Anybody? Anyone, class? Any guess? Why should it not be this? Why should it not be just the sum of your residuals? Why do you have to get the sum of your residuals squared? Okay, Pinying, thank you, Pinying, for your answer. Okay, it's close, but the answer here, class, is that the sum of the residuals will always be equal to 0. Okay, this is the sum. We'll take a look at that later. We'll try to see if indeed the sum of the residuals is equal to 0. So if it's equal to 0, then we can't get any information out of that. Whatever model we're using, then the sum of the residuals will always be equal to 0. So there will be no comparison. That's why we use the error squared. Okay, the residual squared. And then we minimize this. So the model, OLS, takes a look at the minimum. So we write it this way, the minimum of the sum of your residual squared. So this is the model that we use in order to get your ordinary least squares model. When we solve for a linear regression model using OLS, of course, we said that it will determine what's your beta null, what's your beta 1, what's your beta 2, etc., whatever number of independent variables you have. It will now generate the values of your intercept, intercept, and then beta 1, beta 2. Okay, and these betas are unique in the sense that you cannot have any other model with beta null, beta 1, beta 2 having different values and yet have the same minimal residual squared. There's only one and only one model, okay, that will generate beta null, beta 1, beta 2, etc., which will give us the least squares, yung pinaka-konting squares of the residuals. Okay, so I hope that's clear, class. The name itself, ordinary least squares, lend to that notion that we are computing for the squares of what? The squares of the residuals. Okay, so that's what we're looking at here, the residuals. And as I mentioned a while ago, the residuals are those values that are different from your actual values. Okay, we'll have an example of that so that you can clearly see what I mean. Okay, so far conceptually, is it clear, class? May I have a confirmation from your end, class? If the model OLS, ordinary least squares, is conceptually clear to you, that what we're looking for here in this model is to determine beta null, beta 1, beta 2, etc., such that whatever residuals there is, you square it, it will be the minimum. And there's only one OLS model. All right, thank you, good. Okay, all right, so we have loaded our packages. Now we're going to use, okay, now this is the advantage of, let's say the file, you load it in your folder, it will be here, okay? So that when we try to import it to R, okay, we will just make use of the file name, okay? Otherwise, if the data is in another folder, then you will have to identify the file location. Okay, so this makes projects easier to manipulate. So let's create this object. I'm creating this object called wage, and I'm just read. Let's use this read. So you have read.csv, or we have this other read underscore csv. Okay, here. Wait. Read utils stats. Okay, I'm looking for the one under read R package. Okay, here. Read R. Okay, read R and then read READ. There. Okay, there's a package. There's this utils package, and also there's this read R package, which read R comes with the tidyverse. Okay, so this is a better package to use when we're reading files, okay, as compared to the utils package. Okay, all right, so let's just use this. And I suggest that we always use the newer version, the read underscore, compared to read.csv. So here we just identify the file name. If you take a look at your files window pane, it should already be there. So we already loaded this file, so it's very easy to identify it this way. And then if, for example, we can, although that this is the default, header is equal to true, okay, because sometimes your data might not have any header. Okay, so here I'm identifying that each header is equal to true, and then what's a separator? Separator is equal to, it's a comma separated file. Okay, separated by separator. Okay, let's see if this is correct. Control Enter. All right, error. Okay, may mali ako dito. Unused arguments. So dapat yata walang space. Let me check. Okay, read header is equal to true. Kasi may header yung data natin. Separator is equal to comma, since this is CSV, comma separated values. Okay. Unused arguments, header is equal to true. Okay, pag ganyan, what I do, I would take a look at the read underscore CSV. No? Dun sa read.csv, this will run. Okay, let me just try this. No? Read.csv. Okay, from the utils package. So if you take a look at the syntax, the file, the header is equal to true, the separator, and the separator is equal to comma. Okay, so pwede to if you're using read.csv. Okay, so run natin. Okay, take note, it's already here. But just for curiosity's sake, kasi mas maganda rin aram natin yung read underscore CSV from read R package. Okay, let's take a look at how this is run. Okay, here. Read underscore CSV, you have the file. Okay, and here it's using call names, no? Call names, and then what else? There are so many parameters here. Call names is equal to true. Call types, if you want to identify the type of the columns, because if you have several columns, you can identify if one is numeric, one is character, one is factor, etc. Okay, so let's not do that. Let's just run this. And then it does not have this separation. Okay, wala siya, no? Wala yung separation kasi because obviously since it's a CSV, automatically redundant na yung sasabihin yung pa na separator is equal to comma. Otherwise, okay, we could have used this read underscore delim, where we would have identified the lim to be the delimiter to be comma. No? Okay. So, sige, let's run this. I'm going to just use this column names is equal to 3. Control C and not header. No? Header is for the utils package. And then okay, here. All right. Before I do that, I'm going to delete the wage RM and then wage. So let me remove that first. Okay. Once I remove that, it's no longer here in our environment. And then I'm now going to use the, so this should be read underscore CSV. And just to remind us, this is coming from the read R package. Read R package, all right? Read R. Read underscore CSV, wage.csv, call names is equal to true, column names is equal to true. Because our data has column names, let's run this. And then if we check, all right, here. Okay. So, and then there are some information that's given to us here. Okay, rows, 526 columns, 8 column specification, which means you can, here, the delimiter is comma, right? So which means that we could have used this. We could have used read underscore delim and identified the delimiter. So actually read R is more flexible, but you will have to specify more. And then here you have the type of data here. You can identify this column underscore types. Okay, so tatlong character and limang quantitative numerical double. All right, so let me close this. So we now have this wage data set, and it's always good practice to get, let's see, examine the data. So how do we examine the data? Control Alt I. Let's get the structure of wage. So we can see here that it's a data frame. Okay, data frame. And these are the variables: education, exposure, experience, tenure. If we want to view the data, we can use the view function. Okay, and then it will give us this data. And then also can use the summary function, wage. All right, so it gives us the education, experience, tenure. Now race and gender, you notice they are characters, but upon closer inspection, race and gender and civil status is best regarded as factors kasi pwede siyang classifiers. Okay. All right. So for plotting the data, okay. Now the question here is, can we plot the data? Can we plot education and hourly wage? So here, this function will plot education on the x-axis muna, no? And then hourly wage on the y-axis. And then we have main is equal to, this is the name of your plot. So this plot function is from base R. Okay, so the main of the plot is scatter plot of education hourly wage. If we run this, okay. Now why did we generate an error term here? Anyone? Why is this an error term? What's the reason, class? Why error? Why are we not able to plot the hourly wage and education? Anyone? Okay. Thank you, Jonas. No? So, sabi ni Jonas dito, well, hindi nare-recognize ni R. R does not recognize educ and hourly wage. It's not here in your data. And we know this education and hourly wage are from your wage data set. So what we can do is, Jonas suggested that we attach object, or we can just identify that this is coming from wage, okay, and the hourly wage is coming from the wage data set. Okay, so when we do that, that means that we are identifying these variables, education, from the wage data set and hourly wage also. And then maybe we can, let's identify here X. Let's label X lab means X label. X label is equal to our X is, what's our X, class? Always, when you use a plot function, the first one will be your X axis. So X is years. Let's just put years of education, comma, and then let's write here Y label is equal to, just put hourly wage, close. Okay. All right. So take a look at this code now. We're plotting wage. On the x-axis, we have education coming from wage, the wage data. And on the y-axis, we have hourly wage. And then we put the label X lab is labeled years of education, Y lab is hourly wage, and the main plot is scatter plot of education. So if we run this, I'm going to run this. Okay, so we now have here a plot of, on the x-axis is education, on the y-axis is hourly wage. Okay, so kindly chat please if you were able to generate this plot. Okay, good. All right. Let's reserve our comments about the relationship between hourly wage and years of education later. But it looks like, it's difficult to determine whether there's a linear relationship between this. Okay, there seems to be a linear relationship. However, it's really quite scattered, no? Okay. All right. So let's move on. Okay. First, we'll take a look at the linear regression model. Control Alt I. In R, the function to generate a linear model is LM. Tingnan natin to, LM. So this is coming from the stats package, which comes preloaded with R. So LM, no? Ito yung LM is used to fit linear models, including multivariate ones. It can be used to carry out regression, okay, analysis of variance, AOV, and may provide a more convenient interface for this. Now, later on, we will take a look also at another type, the GLM, generalized linear model. This is more powerful, actually. The GLM also comes from the stats package. So the GLM allows us to have to model other types of regression model. Okay, but we'll reserve our discussion on the GLM. Just for you to be aware that it's not only LM, there's GLM and other linear regression models. But as a start, we'll look at LM. Okay. So how do we use the LM function? How do we use the LM function? So let's start with a very basic use of LM function. We're going to use hourly wage, okay, as a uh, education as a predictor of hourly wage. Okay, so the simple function is just LM, and then you identify first your dependent variable, in this case hourly wage. We'd like to know how hourly wage is related to your education, and the LM function that we use is the tilde function there. So hourly wage regress on education, okay, and then we identify the data. Data is equal to wage. All right, so let's first take a look at this very simple linear regression model. Okay. All right. If we run this, okay, what do we have? We have an initial, the initial result. No? LM, so this is the call to the formula, hourly wage regress on education, okay, and then data is equal to wage. And then you have the values of beta null and beta 1. Okay, this is the intercept, and this is beta 1. Now it's better, okay, it's better to create an object for your model. So let's modify this a bit by doing this mod 1. So let's create this model 1, alt minus. Okay, so what are we now doing? We're creating an object called mod 1, and this mod 1 is the output for a linear model where hourly wage is regression education using the data wage. Okay, so if we run this, now we have this object mod 1. And then if we click mod 1, what do you have? So it's a list. It has several elements here. Okay, number 1 is the coefficients. Okay, so if we take a look, if we click this, you will find here the coefficients. Since this is just a simple linear regression model, you have the intercept, and then you have the slope for education. Aside from the coefficient, it also has residuals. There, isn't it that we mentioned a while ago what residuals are? So here we have a list of the residuals. Okay, these are the values of the residuals, which we're going to look at later. There are 526 of them. Since there are 526, okay, there are 526 observations for the wage data set. So we have 526 actual value, and we have 526 predicted value. So when we compare the actual value with the predicted value, then we have what we call residuals. How many residuals? 526 all in all. Okay, so the model 1 object contains several, many elements in it, no? Model, terms, etc. Okay, so in fact, if I write here names mod 1, okay, so let's see what mod 1 contains. It contains this, what we showed a while ago, the coefficients, the residuals, the effects, and we can access this. The fitted values are your predicted values. So aside from your, so we have a vector of fitted values. We also have a vector of residuals. Okay, so we'll take a look at this in a while. And then not only that, we can get the summary mod 1. Okay, this is a very useful output. So let's run this summary mod 1. All right. So what do we find here? Okay, this is quite an extensive output. All right, so let's take a look at this one by one. First, you have the formula that we used. So R revisits this and we say that we're using the LM linear model, where the formula is hourly wage is regressed on education using the data wage. And then here is a 5-number summary of your residuals. So you have your residuals, the minimum is negative 5.3, the maximum is 6.6. So you can notice here that seemingly the residual seems to be not normally distributed. No? Why? Ang layo ng minimum sa sa maximum. Sorry. And then we have here the coefficients. So this is your beta null, this is your intercept. This is the value of your beta null. Okay? And then you have your standard error, the t value, and then your p value. Okay, so I'm sure most probably you have met this output in your previous statistics subject. Okay, so these are inferences, the p-values, and then we're going to identify what are the hypotheses about this. Okay, so while we're here, let's identify for these coefficients, we have the intercept negative 0.90485. So this is your beta null, the intercept. So this is your beta null, okay? Beta null. This one. And this is your beta 1, your education. Since we're only using one independent variable, that's why this is called simple linear regression. Why is this called simple? Because we only have one predictor, education. And the value, average value of education, the slope of education, beta 1 is 0.54. Okay. And then we also have the standard errors, the p-value, and then the probability. Okay. The probability is supposed, before, when there were no computers to solve this, we make use of the t-values and a table to look at the probabilities, the p-values. Because in we use the p-value to make conclusions. Okay? So what's our conclusion here? Ano na oras ba? Okay, wait. I'm checking the time because sometimes I tend to forget. All right, good. Okay, so we have to understand what's the null hypothesis here. So for this one, for this t-test, the null hypothesis is that our beta null, our intercept, is equal to 0. And of course, our alternative hypothesis, so it's HO1, beta null is equal to 0. And so our HA1 is that beta null is not equal to 0. Okay. And also our HO2, our second null hypothesis, is that our beta 1 is equal to 0. Beta 1. Beta 1 is the slope for education. So what's our conclusion? We have here for this first test of hypothesis, the p-value is 0.187. And what's the rule? What's the rule? The rule is that if the p is less than a particular level of significance, and the default is 0.05, okay? So that's the level of significance, 0.05. Then what's the rule? If the p-value is less than the level of significance, then we reject the null hypothesis. But otherwise, if the p-value that we're getting is greater than the level of significance here, the 0.05, then we fail to reject the null hypothesis. Okay, so what's our conclusion about beta null, about the intercept? What's our inference? Do we reject the null hypothesis that beta null is equal to 0, or do we fail to reject it? Class? Notice I'm not really I'm not really discussing this again because these concepts have already been discussed in your prior statistics subject. Okay, so what's our inference, class? Do we reject or do we fail to reject the null hypothesis that beta null is equal to 0? Class? Anyone? Hello, class. Okay. I see here. Evan, do not, bakit Evan do not reject?
The probability is greater than 0.05%.
Okay,
So
so
we do
what,
not reject po.
okay, so what do we not reject?
Um, that the constant or the intercept is statistically different from 0 po.
Okay, so that's correct. Thank you, Evan. So Evan was mentioning that this is our test. We're testing if the intercept, which is your beta null, is statistically different from 0. Okay, or if it's not different from 0, if it's equal to 0. So that's what we're testing. And as I said, here it will use the t-stat, the t-value. So kindly review class yung yung mga basic t-test, okay, z-test. Okay, and then we have the p-value here to be 0.187. And the rule is that if the p is low, okay, if the p-value is low, the null must go. Okay, so I think that's easier to remember. If the p is low, the null must go. Okay, when we say p is low, it means that you're referencing to a certain benchmark, which is the level of significance, which is usually the default is 0.05. Okay, so here our p-value is 0.187. And since this is greater than the level of significance, which is 0.05, then we will fail to reject the null hypothesis. So there's strong statistical reason to believe that our intercept, our beta null, okay, our beta null is not statistically different from 0. Okay, and then how about education? Education is our beta 1. Okay, that's our first slope. And the value of beta 1 is, the average value is 0.54. Okay, we have the t-value here. And then the p-value is practically 0. What does this mean? 2e to the negative 16. So it means you start with this decimal place, and then you go 15 places to the left and write 1. This is, sorry, 2, and you write around 2, because 2 times 10 to the negative 16. So that's practically 0 for all intents and purposes. And the p-value for this one is, since it's practically 0, it's less than 0.05. Therefore, our conclusion is, when the p is low, less than 0.05, the null must go. So we reject the null hypothesis that our beta 1 is equal to 0. There's strong statistical reason to believe that our slope for education is a value other than 0. Okay? So we're rejecting this null hypothesis na equal to 0 siya. Okay? And another part of this summary output is this is your test for the individual means of these parameters. And on the other hand, this one is called your overall goodness of fit. Overall goodness of fit test. Okay? And this is coming from an analysis of variance test, ANOVA test. ANOVA, no? Analysis of variance. and it tests what does this test? So this is overall goodness of fit test or combined test. So it's beta 1 or beta null is equal to beta 1 is equal to 0. Okay, ano yung difference nito at saka nito? So this is an individual test of our parameters, while this is a combined overall goodness of fit test. And once again, if we take a look at this, the p-value here is 2.2 e to the negative 16. That's 0.0000. You have 15 zeros, and then you have 2.2. So that's way, way less than 0.05. So what's the conclusion here? Since the p-value is less than your level of significance less than 0.05, okay, then our conclusion is that we reject the null hypothesis that beta null is equal to beta 1 is equal to beta 2. In this case, walang beta 2, no? Is equal to 0. So we have this overall goodness of fit test. So the conclusion is not all of these are equal to 0. There's strong reason to believe that at least one of these is not equal to 0. Okay. Let me pause for a while. Clear so far, class? You notice, class, I'm breezing through this because this has been discussed in your other subjects. Unless you'd like to repeat something here. Okay, good. Thank you. Is there any part here which you want repeated? Okay, clear so far. All right. Now we'll go back to this and discuss this in greater detail. However, let's just take a look at this. Okay, you have here multiple r squared and adjusted r squared. Okay, 1648, 1632. What's the difference between the multiple r squared? First, what does the r squared measure? Anyone? What does r squared measure? And what's the name for r squared? Anyone? R squared is also called? Okay, it's called the coefficient of determination. Okay, r squared is equal to the coefficient of determination. And what does this tell us? It tells us that, okay, as far as the multiple r squared or the unadjusted r squared, okay, let me just focus on the adjusted r squared because this is more important for us. 16.32% here means that 16.32% of the variation of the variability of your dependent variable, which is what we're trying to describe, can be explained by our model. Our model is using the intercept and education. How many percent of the variation of the variability of your dependent variable hourly wage can be explained by our model? 16.32%. Okay? So what happened to the other 83.68%? Okay, 83.68%. Where is that, class? It means that our model is only able to explain 16.32%, and the others are what we call unexplained variance. Our model cannot explain that. So what's the implication? Then maybe there should be other variables that we can use in order to explain better our dependent variable hourly wage. So using education can only explain 16.32% of the variation of your dependent variable hourly wage. Do you want a better model? Yes. So how can we do a better model? And maybe we use other predictors that have been shown to be have positive or negative correlation or a positive relationship or negative relationship with our object, with our data hourly wage. Okay? All right. So this is just an initial explanation of this. We're going to dig deeper into this later on. So what is our model now? Let me close this. What's our model? So our model is, let me access. Okay, this is where now model will come in very handy. Okay, if we want to access the coefficients, so we can use mod 1, and then if you use $sign, notice that mod 1, since it's an object, okay, it's a list actually. Diba? List siya, no? Yan, no? List. And then if I type mod 1 and then $sign, okay, ulitin ko mod 1 dollar, it will now have this IntelliSense and tell us that these are the objects that come with model 1. So I can now get coefficients, for example, control enter. All right, so these are our coefficients. So therefore, our model is education sub I, okay? Education sub I, maybe we can write this as like this. So $, and then this is, okay, that's your, okay, put the $sign. But this is your, diba? Sub I, no? Education sub I is equal to, so let's copy this. Well, it's, diba, beta null, diba? Beta, diba? Underscore null, okay? Plus, let me copy this, beta 1, control C, control V, beta 1, okay? Multiply that by education. No, sorry. Mali. Okay. What we're modeling is not education, sorry. It's hourly wage. Okay. And then multiply that by educ, right? And let's put educ plus plus okay, epsilon, that's your error term, underscore I. All right. So this is our model, right? Hourly wage is equal to beta null plus beta 1 times education plus epsilon sub I. But now we have the model. And our model is, let's write another equation here. And that let's just replace this. Control C, Control V. Our beta null is, it's now this one. Control C, Control V. Plus our beta 1 is, okay, this one. Control C. Okay, so this is our model class. Hourly wage is equal to 0.90458 plus, etc. Now take note, isn't hourly wage, isn't the intercept not significant? So you might be asking me, why are we including the intercept as part of our model? Okay, the acceptable rule is that if the intercept is not significant, we still include that as part of our model. But if an independent variable is not significant, then we do not include that as part of our variable of our model. Okay, so this is our model. And what we can do now is we will take a look at the residuals, okay? Because we don't stop at the model. Even if we have already identified the model, we said that we have to perform diagnostics for this one. So here we perform diagnostics. What's diagnostics? We check the assumptions. We check the assumptions of residuals. We check the assumptions of the normality of the residuals. Are they correlated? Are they independent from each other? So we can do those checks. All right. So let me pause for a while. Are there any questions so far, class? Class, any questions? Clear so far? And so far, okay, thank you. Good. All right. So I hope the others are able to follow along. Now let's take a look at the. I'm just going to write the code here in the source pane. Okay. So first, let me get the head of mod 1 and then residuals. I just want to get the first 6. Okay, so it's here. Here. I can just run this again. And then, okay, then I can round this off. Okay, anyway, so these are the residuals. Where did they come from? Okay, let's get also the head of the fitted values. Head mod 1, okay, and then there are fitted values, right? Okay, so let me just run this too. Okay, I'm not getting the fitted values. Bakit? Dali, ah. Head, ano mali ko doon? Mod 1, dollar. Sorry. Apologies. It's fitted dot values, no? Okay, so let me change this. Fitted dot values. And then let me just round this round. It's to, let me just round this to, say, 3 decimal places. 3 round 3. Okay, let me run this 2. Okay, so I now have here I now have here the this is the residuals, this one, and this is the fitted values. Okay, let's check where did this come from. Okay, so let's copy the okay, so are we able to get the mod 1? Let me check. Coefficients, and then kasi dalawa to, no? Let's see if we can get the intercept. Coefficients. So 2. Okay, 1. So let me check this. Okay, we got it. All right, what was I doing? We're going to compute now the okay, what will be the predicted value if one has 11 years of education? Okay, so let's do that. So I'm getting mod 1 coefficients, and then let me subset it. Let me subset the first one. The first one will give us the intercept, right? And then if we add Control C, Control V, this time I'm going to get the slope 2, right? Which is the next one is the slope, the 0.5. And then we multiply it by this one, right? Okay, technically you can also get that. You can use the wage data set. Okay. Okay, this is an application of wage data set. And then it's the first row, first column, 1, 1. Take a look at this class. So I'm I'm multiplying, okay? I'm multiplying the slope, the intercept, which is this one, and the slope, which is this one, multiply that by this one, times 11. So that's wage 1, 1. And let's see what the answer is. Okay, so this is the predicted value, which is 5.05. Ito, no? Right? So this is how we got the predicted value. We use the model and then we multiply it, we multiply the different values of education to it. Okay? And then how do we now get the residuals? To get the residuals, we will now compare so from the wage data set, we get this one. This is the actual value, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. So this is the first row and the eighth column, right? And then I subtract that with, we could have created an object for this, but let me just copy this. So this is the long formula class. Control C. And maybe I'll put this in parentheses, which means this is the this is the predicted value. This is the actual value. If I get the difference between them, I'm getting negative 1.9501, which is the residual. Okay, so I just illustrated now how the residuals are computed, how the fitted values are computed. Okay, so you compute for the fitted value, you compare it with the actual value. So actual value minus the predicted value, you now get your residuals. Okay, so let me pause for a while and allow you to, if you're copying, if you're uh, using this formula. Okay, so let me give you a few seconds to work on this. And if you have any questions, please feel free to ask questions now. If you're done, class, kindly please chat also again. Chat yes, so that I know if you're okay. Okay, good, good. All right. So I hope you're following so far. Now, what we did was to have a sample of the computation, but actually we can generate that. So let me insert here. We can, for example, create an object called res, and it will be model one, and then dollar residuals. Okay, here. All right. I'm creating this object called res, and I'm getting it from model one, and specifically the residuals in the list. If I run this, okay, and then I look at this, it's a vector here. And if I, for example, Okay, let's get let's print the rest. It will print all the 526 observations there. So these are the residuals. Okay, and we can verify that these residuals were generated by the actual values, okay, uh, minus the fitted values. Okay, so maybe let's just check. No? Let's just check. So let's call it hourly wage. One, okay, which is just coming from wage, wage, and then let's subset 1 and 8. Okay, so this is a subset of the wage data set. Sorry, not the first row, but all the rows and the 8th column. So this will just give us hourly wage. Okay, so if you take a look, so this one, hourly wage, right? Okay, and then if we if we this time get the say hourly wage hat, which are the predicted values. So this will just be mod mod 1 and then fitted that values. All right. Hourly wage hat. This will now be a where's that? Okay, so we now have this one, hourly wage hat. Okay, so these are the predicted values. So we can now create our okay, resid. I'm just using different names. Resid, which is a vector where we subtract hourly wage 1 minus hourly wage underscore hat. I'm just proving class. I'm just proving that the what will be generated from the res, okay, from the res object. Okay, this one, diba? Si res object is coming from the residuals from model 1. Here, what we're doing is I'm getting the actual value ng wage, and then we will compare it with the fitted values kasi ito yung predicted values, and then we create this object resid. All right. So resid now, this one, these are now the difference between your actual values and your predicted values. So if I subtract, let me just create another object. Sorry about this. If I subtract res minus resid, okay. So this is the data that we got from the model. This is the data residuals that we generated ourselves, right? If we subtract that, then the answer should be 0 class kasi pareho lang dapat yun. I just wanted to point that out. Okay, so where's your R data? Here. And they're all practically 0. Ayan, 0, may mga negative 6 to the negative 16th power, and it's because we were if we round this up round, and then just maybe 4 decimal places. Tingnan natin, ha? Okay. Round natin si res minus resid 4 decimal places. Okay, tingnan natin kung ano nangyari kay. Okay, so all zeros. No? So what was this exercise was meant to at least familiarize ourselves with getting objects or getting data from the model 1. Kasi si model 1 list yan eh. No? It's a list and there are many things there. Okay, so let me sana si model 1 natin? Ito, no? Yan si model 1. So it contains several things. Okay, marami siyang laman, no? So we can make use of that, and later on gagamitin natin yung mga laman niya. All right, then let's go here. How do we plot the regression line? Let's now superimpose our regression line. Okay, we have some more minutes. How do we impose the regression line with our model class? We want to plot. Can we plot the regression line? What do you expect the regression line to be? Class, what do you expect the regression line to be? Of course, it will be a what? A straight line, no? Straight line siya kasi LM model yan, linear model yan. Okay? All right, upwards. Bakit upward sloping? Sorry, Evan, sorry, I forgot to say something, class. I forgot all about this. Yung model natin, ito. Ito, ang ibig sabihin nito, class, yung negative 0.09 na yan. Diba, ang intercept, this one, is the value, average value of our hourly wage when all your predictors are equal to 0. So our predictor is education. Okay? And we're saying that the average value hourly wage of a respondent in this data is equal to negative $0.9 or 90 cent, negative $90 when when he or she does not have any education, 0 years of education. Of course, the practical meaning of this, it's nothing, no? Kasi hindi naman pwede maging negative 9 yung negative 0.9 yung hourly wage. It does not have any practical significance. However, even if the intercept is not significant, then it's still used in the model. Now, punta tayo sa 0.54. No, ito yung sinasabi ni Evan, which is correct. Thank you, Evan, na upward slope. Okay. Paano nasabi ni Evan yun na 0.54, na upward slope yan? Kasi yung slope natin, 0.54, it's positive. So it indicates that there's a positive relationship between education and hourly wage. What does a positive relationship mean? It means that if one variable goes up, its value goes up, the other variable also goes up. Yun ang ibig sabihin ng positive. If the value of one variable goes down, then the other also goes down. So same direction, whether it's going up or going down, they move in the same direction. If it's a negative relationship, that is when your intercept, your parameter is negative. It means they move in opposite direction. When one goes up, the other goes down. When one goes down, the other goes up. Okay, here it's a positive relationship because of the positive slope. And what does this indicate? This means that for every 1 year increase in education, there's a corresponding 54 centavos or $0.54 increase in hourly wage ceteris paribus. Okay, so let me repeat that. Kindly take this down because this will be very important. For every 1 unit increase in education, and education as per our data is measured in years. For every 1 year increase in education, there's a corresponding 54 centavos or $0.54 increase in your hourly wage ceteris paribus. I'm including that term ceteris paribus. Ceteris paribus. Okay. In this case, it might not be significant. It might not be needed because you only have one predictor. But you always normally put ceteris paribus to indicate that you're only changing education and you're not changing the other variables. So what do we mean by that? If Y increase education by 1 year, and assuming that the other variables will not change, they will remain the same, okay, hourly wage will increase by 0.54. That's what we mean by ceteris paribus. So when we have multiple linear regression, when we look at the slopes, we interpret that as the marginal increase or decrease in your dependent variable for every 1 unit increase in your independent variable. So for every 1 year increase in education, there's a corresponding $0.54 increase in hourly wage ceteris paribus, which means you do not increase the other independent variables, that they should remain the same. Okay? All right, it's already time. So just this last one, class, if you need to go, I just want to show you the plot of the regression line. Okay? Kaso medyo mahaba, no? This will take long. Sige, next ano na lang. This will take me mga 5 minutes, no, to plot the regression line. So next meeting we'll continue with this. Okay. So let's just have a quick review of what we have discussed so far. We use the LM function to model a simple linear regression kasi isa lang yung predictor natin. But we learned that in R, when we create an object out of that linear model, it will be a list. It will contain several information, very vital information. So we were able to see the coefficients, the residuals, the fitted values, and among others. Okay, and then we were able to generate the model, the equation for our linear model, and then we were able to interpret the meaning of that. Okay, and we learned that even if the intercept is not statistically significant, we still include that as part of our model. Okay, and we also learned how to interpret the slope for a predictor. All right, so with that, we end our discussion. Okay, so let me stop recording now.